Getting into the topic, how voice assistant actually work, right? This topic might be making you much more curious, but getting into it, you might have made use of Siri, Alexa, Google Assistant, ChatGPT voice, and many other voice assistants. But you could find similar differences in all of them, saying that all are unique to their purposes and functionality. Now let's understand how actually they work. You might have gone through the situation that the voice assistants do not actually listen to your voice always. Rather, they listen to you when you provide a vague word, such as saying, "Hey Siri," or "Hey GPT," or something else. And this is how explaining the process of the voice assistant listening to you as well providing the response. So once the wake word is given, it triggers the detection and then listens to it. Listens to you and then thinks of it through LLM reasoning, like which API to be connected and all, and then acts on it and then provides you the response. So modern voice systems are not single monolithic programs. They are highly orchestrated pipelines of distinct neural networks operating sequentially, one after the other. Now, as I said earlier, it is very much natural that sometimes people think the voice systems always keeps hearing to us. And in that situation, there may rise problems like privacy concerns and all. So that is entirely a myth. And for that, you could also understand constant cloud streaming is computationally impossible. And as I said, it is highly privacy sensitive. So the reality, it doesn't listen to you always. Rather, it listens to you from the moment you provide a wake word. That is, a tiny, low power local loop waits for a specific acoustic trigger. No data leaves the device until the trigger is recognized. Now, audio capture sound into the math. Now, you could also understand the AI assistants, that is, voice assistant, do not actually understand the voice directly. That is, computers don't understand the sound directly. Rather, they understand through the numbers. So the voice that is provided as an input is actually converted into numbers first. So the sound wave is measured thousands of times every second. For example, 16 kilohertz sampling means 16,000 measurements every second, right? The result becomes the voice becoming a huge list of numbers. Something like you can think of taking thousands of photos of a moving car and then reconstruct in the moment, right? Moving ahead. Now, this slide actually explains how speech becomes text. First of all, as you provide an input, your input might include some noise or might not, but it actually receives the input and removes all the unnecessary noise. That is, strips out fan sounds, static, and traffic noise via neural denoising. And the process of removing the noise is called as neural denoising, and then translates the cleaned wave into a spectrogram, the sheet music for neural networks, right? And then getting into neural inference. Models like Whisper or Deep Speech, they actually analyze spectrogram to directly output the text. Now, this is not actually the end. Some models, okay, we'll be discussing in the further slides, that we can actually make use of NLU as well LLMs. But you will have to understand the difference between them and which one has to be used priorly and which one is not. So coming to the traditional NLU, it is the rigid entity extraction and predefined intent mapping, whereas LLM powered, it is fluid semantic understanding via GPT or cloud architectures. That means traditional NLU works using predefined rules. For example, user saying turn on living room lights and then system understands. But what if user says it's too dark in here? Then at that moment, system gets confused totally. But coming to LLM, GPT and Claude or any other LLMs understand the intent. Even if wording changes, for example, it's way too dark here, then LLM understands, okay, the user is facing the darkness and I'll have to switch on the lights, right? So it includes, that is, traditional NLU includes amnesic interactions and forgets prior context rapidly. But coming to LLM, maintains continuous conversation state and resolves complex pronouns. Now, coming to dialogue management and context tracking. It is very much important for any LLM to be remembering the context. And without any context, a conversation goes out of flow, right? For suppose there's a situation where user asks who directed Inception, and then assistant answers Christopher Nolan, and then within the context engine, the entity is extracted, that is Christopher Nolan, and then if the user asks what is his next movie, then assistant might answer The Dark Knight Rises. And in between, what if the user asks who is his over here, or whom is the his word actually describing? Then through the context, the LLM answers here his is the Christopher Nolan. So modern systems do not treat queries in isolation. They continuously parse conversation history, extracted entities, and state to understand relative references. Now, coming to action execution and API orchestration. Now, you might understand that a voice assistant actually listens to the voice through digital numbers, that is, converting them to numbers. And there's a further process in between. But it is also very much important for the voice assistant to actually provide the right answer for the right question. And in that place, the voice assistant acts like an orchestrator, like handling smart home controller when the user asks lights on and all, and also handling the rack database and any other APIs. So you could understand from the picture displayed here, that is the smart home controller through API payload and rack database through vector query and weather service API through external request. All orchestrator responses pass through mandatory content filters to prevent falling devices. Now, text to speech and voice cloning. Coming to text to speech, it converts text into spoken voice. For example, today's weather is 30 degrees becomes a spoken audio. And now, in the modern TTS, that is, in the modern text to speech model, it produces human like voice, emotions, and natural pauses. Alright? Unlike legacy robotic voices, neural systems generate dynamic, emotive human speech. And coming to voice cloning, you might have understood cloning is what making copies of the existing ones. So voice cloning is something that a voice is copied from someone and also generated as much as required. And there you might also face some positive uses. That is, the voice cloning could be utilized in audiobooks, accessibility, personalized assistance, but also have similar risk. That is for deepfakes, fraud, and identity theft. So modern AI can generate extremely realistic voices, creating both opportunities and risk. Now let's go through the 500 millisecond race. That is, as soon as the user provides an input, right, then he actually expects responses almost instantly. That is under 500 milliseconds. But it is very much difficult for the voice assistant to answer in that speed. That is, you could go through the key engineering tension. To feel like a natural human reaction, an assistant must execute all five heavy neural models sequentially in under 500 milliseconds. Slower execution breaks conversation trust, right? So, what is the solution that could be brought in here? Solution is that the streaming method or the modern streaming. That is, AI starts speaking while still generating. For example, AI already sees according to today's forecast and so while preparing the rest of the context or rest of the sentence. And we also have some models that include consuming an audio as well directly responding with an audio without converting into text in between, right? You could also see under the bleeding edge, right? It skips intermediate text translation entirely and lowers latency and preserves subtle emotional cues like size or laughter. Now we'll get into the infrastructure or architecture. That is edge versus cloud architecture. So the edge processing, it runs directly on the device. For example, wake word detection, alarm handling, and all. And the advantages that you could see, it is very fast and private and works offline completely. But also it has some limitations. That is, it is limited to certain computing power. Now coming to cloud processing, it runs on powerful servers. That is remote server. For examples, GPT reasoning, large-scale AI models. It also has certain advantages and limitations. That is, it is very much powerful, but requires internet always. So modern systems combine both. And let's get into the system vulnerabilities and limitations. Now, under the limitations, you could try to understand the acoustic failures presented here. That is, the problems caused by background noise, multiple speakers, and heavy assets. Also, the other vulnerability or the problem that is faced is LLM hallucinations. AI may confidently provide wrong answers, right? Providing some wrong output while having 100% confidence. For example, inventing facts that don't exist at all. Also, the privacy challenges. Users worry about always listening devices, data collection, and recording concerns, for which the solution could be brought in as hardware mute buttons, transparency, and privacy controls being implemented. Now, getting into the production architecture blueprint. Here is the entire process displayed through a pictorial representation, right? So immediately after the user inputs the local mic array and and then the actual unnecessary noise is filtered and then through the wake word, that is wake word detector actually works here and then moves through the bridge to the cloud pipeline. That is STT engine. It might be whisper or deep speech and then gets into NLU or LLM core and then content safety filters and then neural TTS engine. And this process keeps continuing until and unless the user stops providing input. Now, getting into an overview. right? The ultimate mental models. So you might understand how actually the voice assistants work. As soon as the wake word is provided from the user end, then the assistant listens and thinks on it through an LLM engine providing persistent context, intent-person, and open-ended reasoning, and then acts accordingly through external APIs, RAG databases, and all, acting as an orchestrator, and then provides you the output. This five-step pipeline is a precise foundation powering Siri, Alexa, ChatGPT, voice, and the future of real-time AI agents.